If the combat logs from 1942 were entirely accurate, the stern of this destroyer would be nothing more than scattered shrapnel. Instead, high-resolution ROV sonar scans reveal a structure that is more intact than the written record would suggest. This discrepancy between the written history and the physical wreckage is the defining characteristic of the survey of the Imperial Japanese Navy destroyer Teruzuki. We are looking at a crime scene where the forensic evidence explicitly contradicts the witness testimony. The ship rests at over 800 meters in Iron Bottom Sound, and until July 2025, her wreck had never been visually documented. Then, a Nautilus-led team finally imaged her on the seafloor. The Teruzuki was an Akizuki-class destroyer commissioned to protect carrier groups from aircraft, but she found herself running supplies to Guadalcanal instead. On the night of December 11, 1942, she led a column of 11 destroyers on a Tokyo Express run. In the early hours of December 12, 1942, U.S. patrol torpedo boats raced out to intercept the convoy. The engagement was short and mathematically precise. A pair of torpedoes struck her in the stern. The damage severed her propulsion shafts and ruptured her fuel tanks, creating a fire that the crew could not contain. According to the survival reports, the fire raged until 1 a.m. on December 12th when the order was given to abandon ship. The final entry in the historical record states that shortly after the abandonment, the fire reached the depth charge magazine and the stern was obliterated by a massive secondary explosion. For 83 years, historians accepted this verdict. However, the data from the Nautilus survey challenges that narrative. We do not see an obliterated stern, we see a ship that broke under stress but did not detonate. This investigation operates under a specific legal and ethical constraint known as war grave protection. This classification imposes a hard operational boundary. A war grave is not a salvage site. It is a protected location where the remains of the ship and potentially the crew are legally shielded from disturbance. We may not cut steel, we may not recover artifacts for identification, we may not even brush away the silt to read a hull number. The survey must rely entirely on passive observation using lights and cameras to confirm identity without physical contact. This transforms the engineering challenge from one of heavy lift to one of optical precision. We must identify the wreck solely by comparing the geometry of her remaining hardware against the known specifications of the class. This identification process is complicated by a unique historical factor. The Teruzuki was a secret ship. During the war, the Japanese Navy was protective of the Akizuki class, specifically regarding their advanced fire control towers and radar systems. Consequently, no official photographs of the Teruzuki were ever released or archived. For decades, she existed only as a name on a construction manifest and a set of coordinates in a damage report. The video feed from this survey represents the first time the world has ever actually seen this vessel. We are not just checking the condition of a known ship. We are documenting the physical reality of a machine that was previously only a theoretical abstraction. The survey vehicle must navigate a debris field defined by total darkness and extreme pressure. At 800 meters, the water column exerts immense weight on every square inch of the hull. The objective is to document the condition of the main battery, the torpedo tubes, and the controversial stern section without disturbing the sediment that has accumulated over 8 decades. The primary question is not just how she sank, but why the physical wreck disputes the reported timeline. If the depth charges did not explode, then the catastrophic failure of the hull was caused by something else. We must look for signs of structural fatigue, thermal stress, and the specific load path failure that snapped the keel. The investigation begins at the bow. This section of the ship was furthest from the torpedo impact and offers the cleanest baseline for assessing the condition of the steel. As the ROV cameras push forward out of the gloom, we are looking for the twin 100mm gun turrets that define this class. These guns were the primary reason the ship was built, and they remain the most distinct features for positive identification. However, even here at the undamaged end of the ship, the physics of deep water sinking have left their mark. The orientation of the wreck and the state of the forward deck suggest that the journey to the bottom was violent enough to alter the structure long before she hit the seabed. 2,600 feet is a significant barrier. At this depth, the hydrostatic pressure exceeds 1,100 pounds per square inch, exerting a consistent, crushing force on every exposed surface of the destroyer. This environmental constraint defines the condition of the Teruzuki as much as the enemy action that sank her. While the torpedoes caused the immediate loss, the physics of the water column determined how the wreck survived the descent and how it rests today. To understand the state of the hull, we must understand the concept of hydrostatic pressure. As a ship sinks, the weight of the water above it increases linearly. If a compartment is flooded, the pressure equalizes instantly inside and out, leaving the steel plating intact. However, if a sealed compartment full of air is dragged down by the weight of the flooding stern, the pressure differential becomes critical. The ocean pushes in against the air pocket until the steel structures buckle or the seals fail. This is not a chaotic process, it is a predictable mechanical calculation. The hull plating is pressed inward between the frames, revealing the skeleton of the ship beneath the skin. Despite these forces, the forward section of the Teruzuki is remarkably preserved. The survey focuses first on the primary armament. These are the Type 98 100mm dual-purpose guns. They were the most advanced anti-aircraft weapons in the Imperial arsenal, designed to fire rapidly at high angles. On the sea floor, the barrels of the No. 1 and No. 2 turrets are pointing almost directly vertical. It is tempting to interpret this high angle as a sign of a final desperate defense against aircraft. However, the engineering reality is likely less dramatic. These turrets were hydraulically driven. When the ship lost power and sank, the hydraulic pressure supporting the massive gun breeches failed. The heavy breech mechanism inside the housing dropped down under gravity, which mechanically leveraged the lighter barrels upward. This implies that the guns are not frozen in a moment of combat, but rather in a state of mechanical relaxation. The condition of the No. 1 turret provides a critical forensic baseline. This far forward, the steel shows almost no signs of trauma. There are no shell holes. There is no shrapnel scarring. The plating is smooth beneath the layer of marine growth. This supports the historical record that the Teruzuki was not engaged in a surface gun duel at close range. She was ambushed. The violence was concentrated entirely at the stern, leaving the bow as a pristine control sample. Observation at this depth is strictly limited by the technology. We cannot simply look at the ship. We are restricted to the narrow cone of light provided by the ROV LEDs. This creates a tunnel vision effect where we can only analyze one small section at a time. We cannot see the internal decks to confirm if the watertight doors were dogged down. We cannot see the ammunition hoist to see if they were loaded. We are forced to infer the internal state of the ship from the external deformation of the steel. As the ROV moves aft past the No. 2 turret, the structural narrative begins to change. The deck plating shows signs of stress not from explosion but from the torque of the sinking. The ship did not settle gently, it likely hit the bottom with significant momentum. The impact drove the keel into the sediment and sent a shockwave through the frame that snapped the lighter superstructure components. We can see this in the way the deck has buckled near the bridge. The steel has not rusted away, it has been bent by the collision with the seabed. The contrast between the intact forward turrets and the buckling amidships marks the transition into the damage zone. The forward section represents the ship as it was built. The midship section represents the ship as it died. As we move towards the bridge, the clean lines of the naval architecture disappear, replaced by a chaotic tangle of collapsed steel where the command center used to be. The pressure and the impact have conspired to erase the upper works, leaving us with a debris field that requires careful, methodical mapping to decipher. The visual information returned by the survey vehicle is defined not by what we can see, but by the aggressive limitations of the sensor platform itself. Our view of the bridge is limited to the narrow cone of the ROVS-LED array. This is the fundamental constraint of deep ocean survey work. We do not see the ship as a single cohesive object. We see it as a series of disjointed illuminated patches that must be mentally stitched together by the survey team. The light from the vehicle travels only a few dozen feet before it is swallowed by the water or scattered by suspended particulate matter. This phenomenon creates a tunnel vision effect where context is constantly lost. We might identify a hatch or a valve wheel, but we cannot immediately see the pipe it connects to or the bulkhead it serves. Identifying a wreck in these conditions is like trying to map a building by looking through a keyhole with a flashlight. This limitation becomes particularly acute as we move from the main battery to the bridge structure. On an Akizuki-class destroyer, the turrets were armored and structurally self-supporting. The bridge, however, was a lightweight structure built to minimize top weight. It was constructed from thin steel plating and filled with aluminum and brass instruments. Under the dual assault of the 1942 fire and 83 years of corrosion, this structure has lost all integrity. The video feed reveals a chaotic tangle of collapsed metal. Where the command center once stood, there is now only an unrecognizable heap of rusted plating and exposed wiring. This is where the non-intrusion rule of the war grave status creates its hardest engineering challenge. If this were a commercial salvage operation, a manipulator arm could gently brush away the sediment or lift a piece of fallen cladding to reveal the equipment underneath. Because this is a protected site that action is forbidden, we must identify the wreckage strictly by its resting shape. Amidst this confusion of collapse, one specific detail stands out for its clarity. Running along the upper edge of the hull plating is a thick, heavy cable that is hanging loose in the water. This is the degassing cable. In the 1940s, this electrical loop was installed to neutralize the ship's magnetic field and protect it from magnetic mines. It was bolted directly to the hull steel. The fact that it is now hanging free tells us something important about the condition of the ship. The steel hull plating behind the cable has either corroded away or bowed inward under the hydrostatic pressure detached the mounting brackets. The cable itself, protected by thick rubber insulation and made of corrosion-resistant copper, has survived better than the ship it was meant to protect. It acts as an unintentional plumb line showing us where the hull used to be before the pressure reshaped it. Navigating the vehicle through this tangle requires disciplined piloting. The pilot must maintain a safe standoff distance to avoid fouling the ROV thrusters in the loose wiring that surrounds the bridge. This wiring is everywhere. It spills out of the ruined superstructure like a nervous system exposed by decay. In the darkness, these snag hazards are invisible until they are directly in the light pool. A single mistake here could trap the vehicle, transforming a survey mission into a recovery emergency. The collapse of the bridge effectively erases the human footprint of the vessel. The wheelhouse, the chart tables, and the voice tubes are gone or buried. What remains is the heavy industrial machinery that sits further aft. The survey moves past the ruin of the superstructure towards the midship section. Here the architecture changes again. We leave the lightweight command spaces and enter the weapon handling decks. This is the domain of the torpedo tubes and the engine intakes. The structural members here are heavier, and the damage narrative shifts from simple collapse to the evidence of the attack itself. We are looking for the torpedo mount. On this class of destroyer, it was a massive quadruple launcher shielded by a steel housing. Unlike the delicate bridge, this component was built to withstand the recoil of launching 4 tons of ordnance. Its survival or failure will tell us if the fires that consumed the bridge reached the midship's weapon stores. As the ROV pushes aft, the darkness yields a shape that is angular and distinct, marking the transition from the command center to the killing tools of the destroyer. Why does a combat vessel break apart where it does? It is rarely a random event. Steel does not fracture arbitrarily. It fails along invisible lines of stress created by impact and thermal shock. As the survey moves amidships to the torpedo deck, we are no longer looking at the general decay of the superstructure. We are tracing the specific mechanical failure sequence that severed the ship. The centerpiece of this section is the quadruple torpedo launcher. This is a massive piece of industrial machinery designed to rotate and fire 4 Type 93 torpedoes. These weapons were fueled by pure compressed oxygen, making them volatile and prone to catastrophic detonation if struck by shrapnel or fire. Given the reports of the inferno that consumed the Teruzuki, one might expect this mount to be a twisted crater. It is not. The video feed shows the mount sitting intact in its housing. The blast shields are in place, and the tubes themselves are preserved. This offers a critical piece of negative evidence. It proves that the fires amidships, while intense, did not reach the flashpoint necessary to cook off the torpedo warheads. The ship was not destroyed by its own primary battery. The survival of this mount isolates the cause of the ship's destruction to the stern, allowing us to rule out a midships magazine detonation. However, the area surrounding the torpedo tubes reveals the violence of the sinking in smaller details. Near a broken loading davit, the camera picks out a single cylindrical object resting on the deck. It is a loose 100mm shell. This projectile should be in the hoist or the ready locker. Its presence on the open deck suggests it was either thrown free during the capsize or abandoned by a crewman during the evacuation. It is a piece of ordnance, out of place, a small anomaly that speaks to the loss of order as the ship began to list. To understand why the ship ultimately failed, we must apply the concept of structural fatigue. A destroyer hull is essentially a long steel girder designed to flex with the waves. When a torpedo strikes, it introduces a sudden massive point load that exceeds the tensile strength of that girder. But the damage does not end with the explosion. The heat from the subsequent fire alters the crystalline structure of the steel, making it brittle. In the case of the Teruzuki, the hull was subjected to a compound stress test. The torpedoes destroyed the structural continuity of the keel, while the fire softened the steel plating above it. Finally, the uneven flooding created a bending moment where the weight of the water filled, stern pulled against the buoyancy of the air-filled bow. No amount of damage control could alter this physics equation. The steel simply reached its yield point and snapped. This structural failure is visible as we move past the torpedo deck. The plating does not just fade away, it terminates in jagged tiers. We can see the remains of a Type 96 25mm anti-aircraft gun mount that has toppled over. It lies amidst a field of buckled plating where the deck was pulled apart. This is the edge of the cliff. Beyond this point, the main hull ends abruptly. The survey vehicle hovers over the break, looking down into the cross-section of the ship. This is the boundary between the main wreckage and the missing stern. According to the historical narrative, this break was caused by the depth charges detonating. If that were true, the metal here should be shredded outward like a peeled banana. It is not. The break is clean and consistent with a gravity-based structural failure. The hull snapped under its own weight. This observation sets the stage for the final phase of the survey. We must cross the debris field to find the stern itself and confirm the status of the explosives that history claims destroyed it. The stern was found more than 200 meters from the hull. Traversing this gap requires the survey vehicle to leave the visual reference of the primary hull and cross a featureless expanse of silt. It is in this darkness that the final discrepancy of the Teruzuki investigation is resolved. The historical after-action report from December 12, 1942 is explicit. It states that the fire reached the aft magazine, causing a massive secondary explosion that obliterated the stern. If that report were accurate, we should find a debris field of shredded metal scattering for acres. We do not. We find a single cohesive 19-meter section of the ship sitting upright on the mud. This object is the extreme aft end of the destroyer, containing the steering gear and the depth charge rails. Its existence in one piece is the primary piece of forensic evidence that rewrites the end of this vessel. As the cameras push in on the fantail, the lighting array reveals the rails used to deploy anti-submarine ordnance. Sitting in the racks are the cylindrical depth charges still visible on the stern segment. They are not twisted fragments, they are intact. This visual confirmation provides a definitive engineering conclusion. The explosives did not detonate. The crew abandoned the ship believing the stern had blown up, but the survey proves that the noise and violence they witnessed was likely the structural failure of the hull itself, not the ignition of the magazine. However, the condition of this stern section is radically different from the pristine bow we observed in Chapter 1. The steel here is in an advanced state of decay. The plating has dissolved in large, jagged patches, exposing the internal frames to the open ocean. To the untrained eye, this might look like bomb damage, but it is actually the result of a chemical process known as fire-accelerated corrosion. When the fuel tanks ruptured during the attack, the stern was engulfed in a hydrocarbon fire that burned for over 2 hours. This intense heat did not melt the ship, but it did alter the crystalline structure of the steel. It stripped away the protective paint and galvanized coatings and changed the metallurgy of the plates, making them significantly more porous and reactive to oxygen. Once the ship sank and the fire was extinguished, the salt water began to attack this heat-compromised steel. Because the crystalline structure had been altered, the oxidation process occurred at a much faster rate here than on the unburned bow. 83 years later, the result is a section of the ship that looks skeletal. The fire did not destroy the stern in 1942. It merely ensured that the ocean would dissolve it faster than the rest of the ship. This explains the ragged appearance of the wreckage without requiring a magazine explosion. It is further supported by the nature of the break itself. The edge where the stern separated from the main hull is not splayed outward as it would be by an internal blast pressure. It is sheared and buckled consistent with the metal failing under a massive bending load. The stern simply became too heavy with floodwater and the heat-softened keel could no longer support it. It snapped off and tumbled away, landing 200 meters from the rest of the ship. The discovery of the intact depth charges and the identification of the fire damage completes the forensic profile of the Teruzuki. We have confirmed the identity of the ship through its turret configuration. We have mapped the torpedo damage that stopped her. And now we have disproven the myth of the final explosion. The survey has achieved its primary objective. We have extracted the truth from the site without retrieving a single artifact. The decision is made to leave the stern exactly where it lies, observing the strict protocols of the war grave status. The ship has been found, and the record has been corrected. We have verified the identity of the vessel and mapped the mechanics of her loss, but the risk remains active on the seabed. The survey of the Teruzuki concludes not with a recovery operation, but with a risk assessment. The wreck is now a known quantity, a physical object with defined coordinates and a structural condition report. However, the most significant finding of this expedition is not just the steel that remains, but the ordnance that sits unsecured on the fantail. The presence of the intact depth charges creates a complex legacy for this site. To understand the implications, we must look at the concept of ordnance stability over long durations. There is a common misconception that explosives submerged in seawater simply become inert over time. The chemistry is rarely that benevolent. Japanese naval ordnance from this period often used Shimo's powder, which is a picric acid-based explosive. Over 83 years, the metal casings corrode and seawater can interact with the chemical payload. Picric acid can react with the metal of the case or the surrounding hull to form metallic picrates. These salts are often more sensitive to shock and friction than the original explosive. This means the depth charges resting on the stern are not necessarily duds. They are potentially chemically unstable mines that could detonate if disturbed by a grappling hook or a clumsy ROV manipulator. This chemical reality reinforces the operational necessity of the war grave protection protocols. The decision not to touch the wreck is not just a matter of legal respect, it is a matter of physics and safety. Despite the violence evident in the severed stern and the collapsed bridge, the human outcome of the Teruzuki sinking was remarkably different from many of her sister ships in Iron Bottom Sound. The structural failure was catastrophic, but it was not instantaneous. The ship lingered on the surface long enough for the crew to execute an orderly evacuation. The numbers record a survival rate that testifies to competent damage control under fire. Of the crew on board, only 9 men were lost. 353 were rescued by the other destroyers in the transport column. When we look at the twisted metal of the bridge or the snapped keel, it is easy to assume a total loss of life, but the forensic evidence supports the survival statistics. The fact that the magazine did not explode gave the crew the time they needed to escape. The wreck is a monument to a loss of hardware, not a mass loss of personnel. The site is now returning to the darkness, but it is not lifeless. The hard substrate of the destroyer has become an artificial reef in a sediment plain that is otherwise devoid of features. During the inspection of the stern break, the cameras captured a large crab clinging to the jagged edge of the torn hull plating. It sat indifferent to the violence that created its perch. This biological colonization acts as a slow-motion recycling process. The marine life and the corrosion are gradually reclaiming the vessel, turning a weapon of war into a geological feature. This survey has closed the loop on a vessel that was previously a ghost. Because of the wartime secrecy surrounding the Akizuki-class construction, we had no photographs of the Teruzuki before she was lost. She went from the shipyard to the bottom of the ocean without ever being publicly documented. For 8 decades, she existed only as a frantic radio message and a set of coordinates. Now we have the visual proof of her reality. We leave the Teruzuki exactly as we found her. The silt will continue to accumulate, burying the torpedo tubes and the depth charges. The iron will continue to oxidize, dissolving the stern into the water column. But the historical record has been amended. We now know that she did not blow herself apart. We know that the men who survived her were right about the fire, but wrong about the explosion. The difference between the written history and the deep reality is no longer an unknown variable.